Okay.
I have one more question, actually.
Okay.
Do you plan on to do different things if you're going to do 2 classes?
No.
Okay.
Okay. Anything else? How's the homework going? The homework / midterm? I've got a few questions from. Not bad? Not bad? That's good. Did you say not bad or awful?
Not bad.
Okay. All right. Yeah. If you come out of the class being comfortable with the topics on that, then the class has been successful. Okay. Then I guess off we go. Yeah, I've forgotten that I put the capacitance for a BJT on the video, so I apologize for repeating. That said, I'm going to repeat something else that was on the video just to make sure everybody's in the same place. So on the video and on last lecture, we had the emitter, we had the base, we had the collector, we had the substrate, and each one of these PN junctions, nope, no pen. PN junctions, so this is a P and P, and each one of these junctions behaved like a capacitor. So for BJT, there are 3 capacitances that you see. And we'll see why that's important again in a little bit. For a MOSFET, oh, and the equations for these, I'm going to update them. So I've been looking at some of the other documents out there, and so I'll update the equations on the handout. But I gave a few equations. I found out later that I actually took that from my textbook when I took my 306 equivalent. So those equations seem right. I just don't know where the values are in the model file. Okay, so that's BJT, 3 capacitances. And this one's called CCS. This one has 2 names. You can call it, if you forget the name for me, you can call it CBC. Does anybody remember the textbook name?
CMU.
CMU. And then this one, again, if you forget, I'm fine with CBE. But that one has a textbook name too. Remember that one? There's a little bit of memory help here, but if you look at the small signal model, you have the base here and you have the emitter here. And that capacitance goes from the base to the emitter. It's in parallel with R pi. So that one's C pi. Okay. Then, so that's the BJT version. That's on the handout too. Frequency response handout in week 8. So I'm gonna scroll down just to have enough space, or I could do this. Okay, then there's the MOSFET version. And those that had 307 with me, nothing's changed. So you have the gate. You have, we'll call this the drain for no reason. I could have put the drain on the other side. Source. And what happens here is same thing that happened here with the PN junctions. Is this so the substrate would be P-type, and the wells for an NMOS, this would be N and this would be N. Is this junction on or off for MOSFETs? What do you think? This was actually asked, the exams that they give you in grad school, where they put you up in front of a bunch of professors and they just throw questions at you? This was one of the questions that I got asked. Is that junction on or off? So this PN junction right here, so the drain to the substrate or the source to the substrate, are those junctions conducting or not conducting?
Not conducting, right?
Always not conducting. Yeah, so what happens when you have a PN junction that's not conducting? What happens at the boundary?
Capacitance forms?
Capacitance forms, so you have a conductor and another conductor, and then what happens right on the boundary?
Oh, depletion region.
The depletion region. So this is acting just like this boundary right here, and in the forward active region, just like this boundary too. So there's a capacitance here. Wrote them in green in the last one, but oops, still writing in green. So you have a capacitance here, you have a capacitance here, and those are diffusion capacitances, if you give them an official name. So diffusion caps. And that would be your, do it back to black, your C drain bulk. If you used an S for substrate, then it gets confusing whether you're talking about the source or the substrate. So you see dB, and over on the source side, it's CSB for source bulk. And those are formed by the depletion region around a PN junction. Okay, and then there are, when you fabricate a MOSFET, it's kind of naturally you get this, the source kind of seeps under the gate. You can see that the gate's kind of overlapping the source a little bit, and over on the drain side also. That is a conductor, another conductor, and then what goes between the gate and silicon?
Dielectric?
Dielectrics, silicon dioxide. It's an insulator in this case. Yeah, silicon dioxide is dielectric. It is, right? It behaves as a dielectric with a capacitance. Yeah, okay. But you get another parallel plate capacitor that looks like this. And this one, it's to differentiate it from other capacitances. This is overlap cap, but it's a physical capacitance. It's exactly what you see in a textbook as a parallel plate capacitor. So this is physical capacitance, capacitance, and those two capacitances are C gate drain overlap, so that OV. There's also gate drain capacitance, so to distinguish it from that capacitance, you use the overlap, and that means it's those little ends that are overlapping the source and drain. And you have C gate source overlap. Okay, and then the last one is channel capacitance, and that is just C gate channel. And what that means, and in different textbooks, they'll call it, they'll actually call it gate, oh, a big bird just flew into my tree, gate drain or gate source capacitance. And that's where you can get it confused with the overlap. And that's why it's safer just to call it gate drain, gate source overlap and gate drain overlap to distinguish it from what textbooks call this channel capacitance. But that right there, the gate actually couples to, in the forward active region, it couples to the electrons in the channel. Okay. In other regions of operation, this gate channel capacitance is a little bit different value. But for us, in the saturation region of a MOSFET, it's coupling to actually the electrons that have gathered in the channel. And for these equations, they're also on the handout. But I'll just really quickly. Yep, this side should go. Oh, wrong one, wrong one, wrong one, wrong one. Okay. Do things slow down a lot when you're using Zoom?
Yes.
Okay, I'll just draw it out then. So we'll do the easy ones first. So gate channel overlap, 2/3. It's the area of the gate. It's 2/3 of the area of the gate. So you know the width of the gate and you know the length of the gate. So the area is just width times length. And then that gets multiplied by this thing called Cox. And Cox equals Eox over Tox. Your Tox comes from the model file, as so many things do. Eox is, you have a free space value of this, and I put it, I think, on the handout. Let's see if the handout's up. That'll be quicker. The handout's quick. Why didn't I think of that? Okay. And, oops. Okay, now I broke Word. But for silicon, okay, well, I broke Word. This is 3.9. It's a constant, and this is in free space. And what is it, 5 point, who knows off the top of their head? 5 point, yeah, I broke Word. Okay. But those values are on the handout. Okay. Gate drain overlap and gate source overlap. Those are friendly equations too. It's W times, so gate source overlap, W times CGSO. So if you look in the model file, again, the model file, there's a value for CGSO. You just multiply that by the length and you get the capacitance for the gate source overlap. And gate drain overlap is the same thing. Just W times, instead of gate source overlap, you go to the model file and look for CGDO. Okay, so this is actually a bit more complicated. The source and the drain it's the same equation. So I'll just write it once because it is complicated. But you just, depending on what level your model is, sometimes they separate the drain and the source values. So there'll be two values in the model file that are different. One's for the source and one for the drain, but the equation's still the same. So for that, we'll go, and if the device is symmetric, then your drain bulk will equal your source bulk. And that equals 2. The two things. If you look at the source or the drain, they're kind of shaped like a box. So I have it all rounded here, but these actually go back and up, and you've got kind of a box shape here. And it turns out there's a bunch of capacitance on the bottom, and there's a bunch of capacitance on the side. If you've heard of fringing capacitance, it's just around the outside of something. Think of this, the capacitance on the side of this thing, kind of like fringing capacitance. And the bottom is just really a parallel plate capacitor. So the bottom area of this, you notice if you look at how I drew this, you can tell that the gate width here, so this is the width of the gate right here, that's the same as the width of the source or the drain. So the width of the source and drain are the same as the width of the gate. But this distance right here, that is clearly not equal to the length of the gate. So this is the L, this is the length of the gate right here. And that's clearly different than the length of the drain. So when you use these equations, somebody has to give you the length of the drain. You can't use the L from the gate. And so when you're calculating the capacitance on the bottom of the source, in other words, on the bottom of that box, it's the area of the box. So it's whatever the length of the drain is. I know I have the source in here. I'll put parentheses around source because I'm going to use, I'll use D as the subscript, but I mean it would be an S for the source. And you know the width of the source or drain is just W. So as long as you have this length and W is going to be the same as the gate, then you can find the area. And then you multiply it by Cj. And guess where you find Cj?
The model file.
Yes. Okay. So this goes in the model file. And excuse me, I was just eating some seaweed. So if I have big black spots on my teeth, that's didn't lose a tooth. Okay. Yeah. And so that's the bottom. But now you still have to find the capacitance around the outside. And this overlap right here actually takes care of this inside side of the source or drain. So both of those are already taken care of. So you only really care about three sides: the front side, the back side, and the outside side of the source and drain. And for that one, you say, okay, I want to know what the capacitance that's caused by this side of the drain, this side of the drain, and the back side of the drain. So you add up the length around that outside. So how do you find the length of that outside? If you walked from this point to this point, and then you walked from this point to this point, and then you went around the back side and walked across the back, what would that total length be? What do you think? How far is it to walk across the front?
It would be the LD. So I think total it's 2 times LD plus 2 times the width.
Okay, it would be 2 times the width, but you get to ignore where the
okay.
overlap is. That's already taken care of. So you get to ignore that, but perfect. Yeah, this times 2, I should have put the 2 first. 2 LD. That takes care of the front side and the back side, and then you still have to take care of this outside side. So that's just W. And this is CJ sidewall. And guess where you find that?
Model. Wow.
Yes, exactly. And so now you can find any one of these capacitances. And these are the 5 names I'll use for the capacitance for the MOSFET. Remember, there are only 3 for the BJT, but there's 5 for the MOSFET. Okay. Any questions on where in a transistor where capacitance comes from and the equations to find that capacitance? You can find much more complicated equations, and you probably use them in 306, but when the voltages change, the capacitance changes. These equations right here are a good enough approximation for you to tell, be pretty close to the capacitance on your transistor. It's not going to be super accurate, but let the simulator do that hard math for you. Okay. So any questions on this? I interrupted myself when I was asking y'all. Okay, so let's see how to use this. Let's take, got some pretty pictures here. Oh, I didn't write the names of the capacitance in here. Right, so if you have a snippet or something, capture this picture so you have the names of the capacitances for the two types of transistors. Give you 10 more seconds. It's also on the handout, but my handout's dead. If I close some applications, yes, true. When I bring up a tab, it's my reminder to do something. So if I close it, then I often forget to do stuff. I know it's not the most, it doesn't make my computer very happy, but okay, everybody got a picture of this? Okay, so now let's go find, let's make this bigger. And we're gonna do kind of a one run through, and then we're gonna fix these answers. So right now, we're not doing exactly the complete story, but let's give it a go. So here's my question to you. If somebody asks you for the capacitance on Vn, so CVin, the way you do that is you'd go back up to, since this is a BJT, you'd go back up here and you'd say, Vin is on the emitter. So you'd come to this picture and you'd put yourself on the emitter. And then if you are on the emitter, what capacitance is directly connected to the emitter?
C pi.
C pi. And all of these others, yeah, you could say, oh, they look like they're in series, but you don't count those. You only count the capacitances that are directly connected to the emitter. So CVin, C pi, and I'll do our first pass in red. Okay, what about CV out? And to find the capacitance, you have to go in all directions. So the first direction you might go is up and hit the resistor. How much capacitance do you see there?
No capacitance?
Yeah, we'll treat that as ideal. Since it's a resistor, we'll say no capacitance, but resistors in integrated circuits do have capacitance. And so they actually have their own frequency response. But yeah, so there's no capacitance looking up. So let's do CRC. That's 0. Is that more confusing to write that in? That's what I think it is. So 0 for looking up. What about looking down? What terminal do you hit?
The collector.
Okay. So then once you identify the terminal, go back up to this picture and you look at the collector. What capacitances are directly connected to the collector?
C mu.
C mu?
And CCS.
Exactly. C mu plus CCS. And you have the capacitance on the terminals, kind of. Okay. Actually, in this case, that is the capacitance. So both of those are accurate. Okay, how about over here? Here's a MOSFET. You can tell I just kind of did a little erasing and threw a weird thing on the gate. But that's these are supposed to be MOSFETs over here. So what's your V in for the MOSFET? First of all, identify what terminal you're on. So what's the input terminal?
Source.
Source. So then if we go back up to the MOSFET, if you're on the source, I see two capacitances directly connected to the source. What are those?
CSB.
Okay, source bulk.
And CGSOV.
Perfect, yeah. So back down here. So you have CGS overlap. It'd be nicer if I could keep them both in the picture, huh? And then CSB. Okay, what about V out? So looking up at the resistance, again, we'll call that ideal. Then looking down, you hit the drain. So go back up here. I'm sorry for all the scrolling here. It's not good style. On the drain, what do you see? What capacitance do you see on a drain?
CDB and CGDOV.
Perfect, yes. So you see the gate drain overlap and you see the drain bulk capacitance. So that is C gate drain overlap plus C drain bulk. Okay, and these are actually correct for even what we'll talk about in a minute. Okay, so any questions on how we got the capacitances for these two? For the common base and the common gate?
Why is it again that you can just ignore the other capacitances?
They make little difference. And these are, again, if you look at the equations for capacitance, let's see if I, Avante. Nope, not that one. Avante, Spice models, nope. Launch meeting, nope. Okay, never mind. Take me longer to search for it. But if you look at the equations that Spice uses, they're horribly complicated. These are tried and true equations to approximate that capacitance. But the in series, let's say you go back up to the BJT, if you just take this capacitance, it turns out this capacitance right here just really doesn't make all that much difference in this capacitance, experimentally found to not make all that much difference. So you can always make it more complicated, but you don't get much of a benefit by considering all these in series. So maybe not satisfying, but just known from experimental and many years of use that if you just take the capacitance that's directly connected to a terminal, that is generally good enough to be pretty darn close. And then you have diminishing returns as you make it more complicated. Okay, so now that you're masters, let's go on to the one that we'll have to fix in a minute. Actually, let's move this out a little bit. Let's do this amplifier. So we're looking for C, how about C in? And C out. So how about giving everybody a chance to give that a try before? See if this will fit someplace. Okay, let's give this a go then. For C in, what did you get? So first of all, oh, go ahead. Go ahead.
C pi plus C mu.
Okay. Yes. So let's check this out. The inputs on the base. So you're here. So you only see these two capacitances, and that's C pi and C mu. So exactly C pi plus, and I'm gonna leave a little space here to fix it in a second. And what about C out? What'd you get for C out?
Is it CCS and C mu?
Yep. So even though C mu was used on the input, the output also sees that capacitance from the other direction, but it still sees it. So both of those are okay. So let's give this in person. It's better, but and those that have heard of the Miller effect, this will make sense, but never tried this on Zoom. So there's this thing called the Miller effect. And the Miller effect happens when you have a capacitance between two nodes that are moving. So for a common emitter like this, the V in might go up this much, V out goes down a lot. So V in goes up by this much, but V out goes down by a lot. So when you have both sides of a capacitance moving, and remember this for V in, you're on the base, and so this C pi, oh, that goes to the emitter, sorry. This C mu goes from actually the input to the output of your amplifier. And you know, if you move the input, the output moves. Okay, so both sides of that capacitance is moving. So what's happening here is this side of the capacitance says, I've got to move up by delta V. And do you remember this equation? This pops up a lot. And what this Q is actually the difference in charge across your capacitor plates. Okay, so it's not relative to anything. It's relative to the other plate. So how many more electrons do you have than I have? That's what this Q is. So it's actually more like a delta Q. And this voltage is actually the voltage across the capacitance. So it's actually like a delta V. It's the voltage across the capacitance. So voltage on one side minus the voltage on the other side. Okay, so when V in, I'll be V in, so that's I. When V in moves up by delta V, it says, I've got to change my side of the capacitor up by delta V. I have to change the voltage on my side of the capacitor. It has to go up by delta V. So if I was just had a capacitor connected to ground, say I just had not this capacitor, because this one, both sides are moving. But let's say I had a capacitor connected to ground and I needed to raise the voltage by delta V, I'd put delta Q on. I'd put some amount of charge on there and to get that voltage to go up. Okay. So up to there, good? Thumbs up? Okay. So, right, so if I move this up and the other side's not moving, I just have to put up enough charge to make this voltage across the capacitor change by delta V. But if the other side is moving away, let's say I didn't do anything and the charge didn't change, the voltage on my side would be going down. So if you had a capacitance and there was no place for the charge to go on either plate and you lowered the voltage on one plate, the other plate would go down. Okay. So let's look at what happens here. If this goes down delta V, how much does V out move? Let's say the gain of this thing's AV. How much does V out move? Do you agree? I'm going to put an absolute value around it just to make sure that the signs make sense. So if this has a gain of 100 and I move this 100th of a volt, the output should move 1 volt. But since it's inverting, it's moving in the opposite direction of the input. Okay, so here we go, one more time. So we have our capacitor between V in and V out. And V in is trying to go up by delta V. But when it goes up by delta V, the other side of the capacitor goes down by AV delta V. Right, so if this just put enough charge to change its side by delta V, then it would go up delta V, but the other side, when the V in moves by delta V, the other side moves down by AV delta V. Is that picture okay? Okay, I got 1 thumbs up. Okay, let's see, so 2 pictures here. If there's no place for the charge to go, so there's no change on the plates, and I move the voltage down on one side, do you agree the other side has to move down? Okay, so if I move voltage down on one side and there's no place for the charge to go, you still have the same delta Q across here. So the voltage across it still has to be the same. Now let's say the V in, it says, oh, I've got to move up by delta V. Let's assume V out doesn't move yet. I put enough charge to change this delta V. But when V in moves delta V, V out moves AV delta V down. Does that picture work?
Yes.
Okay. All right. So what happens is V in gives enough charge to change delta V, but then because V out moves, pulls V in down, and V in says, oh my goodness, I've got to put a whole bunch more charge on this to get it up. I'm trying to raise my V in up just delta V, but it just sunk. So I have to put a whole bunch more charge on there to get it to go up to that V, the original V in plus delta V. So I have to put enough charge to not only change it delta V, but counteract the other side of the capacitor moving away from me. How's that? No thumbs up on that one. Okay, let's see.
Wait, so where's this charge coming from? I know delta V is skyrocketing because of the increase in okay, there's two delta V's right now. I'm talking about the delta V in the equation, like the across the capacitor.
Okay.
That's increasing a great deal because of that slight increase in delta V earlier, and then the corresponding decrease in V out, causing that overall voltage across the capacitor to increase. And then that capacitance is going to stay the same, I'm assuming, and so that means that delta Q needs to increase because of it, and that's why you need the charge. Is that what you were saying up until now?
Yes, a lot of current has to come in from V in
Okay.
to counteract. So the capacitance, the V out's trying to pull down your V in value, but your V in value is actually trying to go up by delta V. So it has to counteract a V out going down, plus it has to get up to delta V higher than it originally was.
Okay. Okay, that makes sense.
Okay, got one okay.
Bad thing? Is that a bad thing though? The like, large need of current for at the input?
That's okay, but if you're standing on the input and see that much more current going in, you're saying, wow, that's a big capacitance. Well, actually, it's just a little capacitance. It just so happens that the other side is moving away from you. So we have to put a whole bunch more charge on it. Even though it's a little bitty capacitance, it's going down and you have to charge your side up so much more. Your little capacitance looks like a giant capacitance.
Okay.
So if this goes up delta V, so let's say this goes up delta V, and the other side of the capacitor goes down AV, and again, I'll put absolute values signs on here, delta V. What's the total change in voltage across that capacitor right here, this capacitance? What's the total change in voltage? This side went up by delta V, this side went down by AV delta V. So what's the total change in voltage?
Delta V times 1 plus the gain in all
Yes.
parentheses.
Yeah, I'll put that in again to get rid of the. Okay, so your V in's trying to just move at delta V, but because the other side's moving away, the actual net change in voltage across that capacitor is actually this thing right here. What do you think? Any thumbs up? Okay. All right. So because on the input side, you had to put 1 plus AV times more charge onto that capacitor actually looks like it's 1 plus AV times bigger. The voltage changed 1 plus AV times more than your side is changing it, trying to change it. This is hard even in person. But let me do the, let's move this out. So this equation that we first wrote up is actually not correct. This capacitance right here, because the other side of it is moving, actually looks, if you're sitting on V in, you have to put so much more charge on it to get it to go up to the voltage you want it to be, that it looks like a capacitor of size 1 plus AV times bigger. I think this isn't working. Anybody want to try to give this an explanation? Okay, the only time you'll see in the next couple of equations too that some of the capacitances have multipliers. The capacitances have multipliers when both sides of the capacitor is moving. So let's see, anybody want to give this a try? Okay, I'll give you the conclusion. This is called the Miller effect. And the Miller effect says if you put a capacitor from the input of an amplifier to the output of an amplifier, it looks AV times bigger. So if you look over here, if AV is 100, 100 plus 1, it's kind of the same thing. So yeah. This is called the Miller effect, and it just means if you're on the input of an amplifier, any capacitance from the input of the amplifier to the output of the amplifier looks bigger by a factor of 1 plus AV. Strange. So, let's see. How about, I know it's time, but if you have time to stay, how about 2 questions? How about 2 questions? If you have to go, that's fine.
I have a question. Does that mean that C out, the only change, it's just going to be the same change, right? Because
Not though, because
Oh.
on C out, if C out moves delta V, or V out moves delta V, how much does V in move?
delta V divided by the gain. So
Yes.
not,
So if you really want to be, sorry. Because your side moves delta V, the other side moves 1 over the gain. It moves less by whatever the gain is. But usually people ignore this and say, oh, 1 over 100, that's nothing. And just say, oh, it's CS plus C mu. If you really want to be annoying, you can put this in, but it doesn't give you much, it doesn't change the result much. It's a good approximation to ignore that.
okay, I see. So, I mean, would it matter in terms of like really small gains then? Like if you had something that was slightly, or even with a CC fire, for example, that's a gain of 1. So you're increasing it by a factor of 2. So would it matter in that case then? Or is it just like we don't care about it in general?
You picked another circuit I was going to do. I was hoping to get there, but we didn't get there. But let's see, what is the voltage change across here? We'll do it better next time. But what is the voltage change across from V in to V out? If V in moves, what happens to V out?
It also moves the same.
Yeah. So is there a voltage change across the capacitor?
No. I thought it would be the VB on.
There's a DC voltage, but does it? So the reason with the common emitter that you have that issue is because both sides are moving in opposite directions, and the actual voltage change across the capacitor is much bigger than the change on the input.
Okay, so we're looking at it in terms of change in voltage, and then
Yes.
that make it 0 across there then.
Yes, and if there's no current going on to it, it's like an open circuit. So you actually get to ignore any capacitance from the base to the emitter on a common collector. You get to ignore it. So it's great for frequency response.
Okay.
That capacitance just disappears.
Okay.
Everyone's still here. I guess maybe I should have done that more gracefully, but okay. See, how about one more question? Who else has a question? Oh, okay. So this is a way in integrated circuits, capacitors are really large. So you can use this trick. You can use the Miller effect to make a small capacitance look really big. You just put it across an amplifier with a big gain, and it looks like a big capacitance. Kind of cool. So let's see, any other questions? I see people still here, so if you have any questions.
Can I ask, does the like capacitance like ever have an effect on like loading of circuits?
Yes, at higher frequencies, current goes on to them and off of them. And that's why sometimes when you see like even a common source amplifier, you'll see a resistor on the input, but gates have infinite resistance. So why would you need a resistor? It's because there's capacitance here and current goes on to that capacitance and off of that capacitance. And you can get rushes of current going into the gate. So even though there's no current going through the gate because there's capacitance on it, at high frequencies, you get current going onto this and off of it. You get really large currents going into the input of a MOSFET.
So would that slow the circuit down, adding that resistor there?
It would filter. So yes, you're making the RC. So before you add the resistor, you just have the resistance of the wire. And remember, a corner frequency is 1 over RC, so a really small R puts that way out at a high frequency. So at least your gain is affected. But anything that filters also delays in my touchy-feely world. Any other questions? You're all welcome to stay for a second hour.
Thanks, Professor.
All right, I'll see you later.
Thank you.
All right, bye-bye. I might just use these scribbles just because they're nice instead of redoing the scribbles. I didn't see Raul in the last section. I'll pause the record. All right, so just yeah, I'll use the pictures from last section just because I kind of drew well and my pen's not working, so it's a pain to write. But last time we looked at the BJT, and BJT has 1, 2, 3 PN junctions. And so how many capacitances does it have, naturally forming capacitances?
3.
3.
I
So,
have a question.
okay.
What defines a capacitance? Is it like the flow of electric fields from one channel to another?
These actually form because the collector substrate and the base collector junctions, because they're not conducting, you get a depletion region. So you have a conductor depletion region, which acts as an insulator, and then another conductor, and that actually forms a capacitance.
Oh, got it.
Okay, and then the BE junction, that one is forward bias, so it's conducting, but there's it takes some time for the electrons to redistribute themselves, and it looks like capacitance. It acts like a capacitor, so it's considered just like we've been using transistors as resistors. It looks like a big resistor or it looks like a small resistor. Because of the time it takes for electrons to redistribute themselves, it looks like a capacitor. So we have an equation for what capacitance it looks like. And those are on that handout, frequency response handout. So we'll go through that. And oh, that's right. And those equations actually came from my class, my 306 equivalent class. So those equations are valid. I'm just still not sure where in the model file those values are. So I'm either going to change those or figure that out. I just have to find my textbook again. And I'll kind of update that frequency response handout. Okay, and so there's 3 capacitances. I have them drawn in green here. And for me, it's fine if you call this capacitance CBE because it's between the base and the emitter, or this CBC because it's in the base and the collector, or CCS because it's in the collector to the substrate. But in textbooks and possibly in interviews, you probably want to call them by their kind of traditional names, which is for CBC, it's C mu, and for CBE, it's C pi. And a good way to remember that is if you remember the small signal model. So for the small signal model, you have the base, and then there's R pi, and then there's all the stuff over here. This is the CBE capacitance right here. So it's this capacitor right here. It's in parallel with C pi, so you can remember that one's, sorry, it's in parallel with R pi, so you can tell that one's C pi. And then the one that's left over between the base and the collector, that's your C mu. And we'll actually work with the small signal model with these drawn in. Soon. I'll move the substrate up a little bit here. But yeah, the C pi is in parallel with R pi. And then from the base collector, that's your C mu. Okay, so that was the BJT. For the MOSFET, it's more complicated. Okay, and again, just I think I already said it, but the equations for finding the value of each one of these capacitance, that's on the frequency response handout. Okay, for the MOSFET, you've got your gate, you've got your source, you've got your drain, and I'm drawing this a little bit prettier. Okay, so oops. Got the gate, and the gate is not in silicon. What's between the gate and silicon? Remember?
Nothing.
There
Oh,
are.
Insulator maybe.
It's an insulator. Yeah, it's silicon dioxide, and so you have your gate which conducts, and then you have an insulator which doesn't conduct, and then you have these little areas right here where the drain kind of seeps under the gate. So you have the gate and the drain, or the gate and the source. They overlap a little bit, and that is kind of textbook parallel plate capacitor. And these are overlap capacitances, and they are called physical capacitance because it's just like a parallel plate capacitor. And their names are your gate drain overlap on the side where the gate overlaps the drain, and your gate source overlap, which is where the gate overlaps the source. So these are these two little red capacitances right there. That's the gate drain overlap capacitance, the gate source overlap capacitance. And these have a nice friendly equation to calculate capacitance. These, when you're actually operating a transistor, the capacitance changes. You can use a transistor as a variable capacitance, like a, potentiometers for resistors. You can actually use a transistor as a variable capacitance capacitor. So the capacitance changes. So these equations are just approximations, but they're pretty good approximations to get you in the ballpark, and you can just you can get enough information to see if something's going to run at the frequency you want it to run at, things like that. So again, these are simplified, super simplified equations and just ballpark. But your gate source overlap, so in other words, where the gate overlaps the source, these, you can see that the drain and the source, their width is actually the same width as the gate. So this width right here is considered the same width as the gate. Where it sticks out farther, that's not considered part of the source anymore. It's considered something connected to a source. But if you notice the length of the gate right here, it's not the same size as the length of the drain. So the length of the drain is across here. That length is not the same length as the gate. So the width of the source and the width of the drain are the same as the gate. But the gate length and the source length or drain length, those aren't equal. So somebody actually has to give you this. This must be given to you. Must be provided. If that makes sense. Somebody has to give that to you or you can't calculate capacitance. So this width right here, which is the width of the gate, to find the gate source overlap, you just take that width, because that's how long it's overlapping for, and you multiply it by this thing from the model file called CGSO. So it's a super simple equation. Just take the width of the gate and multiply it by this value from the model file, and you're done. You've got your capacitance for that overlap. So good up to there? Okay. And nothing new on the gate drain overlap. The only difference is that you still as wide as your gate, but now in the model file, you look for a different value. You look at the gate drain overlap value. Okay. So check on the overlap capacitances. Okay. Right. So let's do gate channel. So there's the gate couples to the substrate. It has different capacitance depending on which region of operation you're in. But in this class, what region of operation do we want all of our transistors in?
Forward active.
Forward active. So we get to kind of ignore the other regions of operation. And for the forward active region, or in this case, since we're MOSFET saturation region, it's 2/3 of the area of your gate. And you know the gate has a length of L and a width of W, which that's weird looking. So the area is just W times L. So you take 2/3 of that and times the area, 2/3 of the area of the gate, and you multiply it by this C aux. And C aux is your dielectric constant, right? I blanked on the last class, which is free space dielectric constant times 3.9. It's a constant. and then it's divided by TOX. And guess where you find TOX?
The model file.
Model file. Yeah. So this relative dielectric, that's a fixed value for silicon. If you're using gallium arsenide transistors, it would be a different value. But for silicon, it's always 3.9. And this free space, that's always a constant. So that's where that comes from. And that's this capacitance and the gate to the channel. So gate to whatever's underneath it. It's actually coupling to electrons when it's in the forward active region. The gate forms, it's not coupling to the silicon exactly. It's coupling to the electrons in the channel. Okay.
I have a question about that.
Okay.
When you say it's not the silicon, are you talking about the atoms that are not, or are you talking about the electrons that are not in the silicon atoms that are instead like free flowing electrons?
Pretty
that
much.
Come from. Okay.
Yes. For an NMOS, sorry, I should say for a PMOS, it's holes.
Okay.
And if you remember that when you're in the forward active region, you get a collection of electrons over by the source, and then you have a region here that's a pinch-off region. So this these electrons that are kind of leaning over towards the source, that's what the gate couples to.
Oh, got it.
Okay. So this equation's friendly too. 2/3 of the area of the gate times this COX. And TOX is usually nanometers. And then comes the messy one. Okay, so we've done the overlap capacitances into the channel. The last one is from the source to the substrate and the drain to the substrate. And first question, this is a PN junction. Is that PN junction conducting or not conducting? So the drain to the substrate and the source to the substrate. Are those conducting or not conducting?
Not conducting.
Not conducting. Always off for MOSFETs. And when you have a PN junction that isn't conducting, what forms at the boundary?
Charge.
Or it's actually lack of charge. So it's
depletion region.
Yes. I wanted to play the sound game again. Yeah, so it forms a depletion region, and then you have a parallel plate capacitor again. So these right here, we had physical capacitance, that's textbook parallel plate. That's the overlaps. You've had channel capacitance where it's actually coupling to electrons. This is a different kind. This is a diffusion capacitance, which means it's a capacitance formed by a depletion region. Okay, now this is a messier equation. You can tell by the scribbles up here. But if you look at the source and the drain, they actually kind of look like a box. And they look like a box where there's some capacitance on the bottom and there's some capacitance around the sides. So if you imagine a box, the bottom of the box is just a parallel plate capacitor again, but the sides of the box, they're kind of more like fringing capacitances, if that sounds familiar. Okay. So you have to actually calculate the capacitance on the outside of the box differently than the bottom of the box. Okay. So when you calculate the capacitance of the bottom of the box, you use the area of the source or the area of the drain. So if I called this length right here, remember it's not the same as the gate. The gate length is from here to here, but the source and drain length, that's from here to here. And let's say I call from here to here, LD for length of the drain. What's the area of the drain?
LD times W.
Perfect, yeah. So that's the area of the bottom. And since it's a parallel plate capacitor, take the area of the bottom, so that's the area. And you multiply it by CJ. Guess where you find CJ?
Model file.
Model file, yes. Okay, and that gives you the capacitance on the bottom, but that's, you still have to add in the capacitance around the outside of the box. And one thing tricky here is that these gate source overlap and gate drain overlap already take care of the side that's underneath the gate. So you get to ignore that side of the box. So you only have to worry about 3 sides of the box because one side's already taken care of. And you look at how long it would, what the distance is if you walk around. So you'd go across the front and then across the outside side and then around the back. So there's 3 sides. And what is the distance if you walk across the front, down the side, and then across the back? What's that distance that you just walked?
2W plus 2L.
Okay, but one of the W's, again, is underneath the gate. So you get to ignore that. So exactly what you said, and then minus one of the W's, and you get the distance across the front, which is LD, plus W, that's walking along the side, and then 1 LD across the back. And you multiply it by CJSW, which guess where you find it? All together.
Buried on an island underneath like an X or something like that. No, the model file.
Yes. Yeah. But that's a much better answer. Yeah. And so that's the equation for either the source or the drain. But again, somebody has to give you this LD or this LS before you can use that equation, because it's not the L from the gate. Okay, so now at this point, hopefully you've seen where the capacitance comes from in a BJT and the equations for that capacitance, and where capacitance come in a MOSFET and what the equations for those capacitances are. Any questions on those? Okay. All right, we're doing something more fun now. I mean, not woohoo, but more fun. Let's grab these. And let's go over here. And I'm gonna be scrolling up and down here, so I apologize for that. I could get rid of some of this. Channel, no. All right, so first question is, I'll do the first one with you. So what kind of amplifier is that?
Common emitter. Oh, wait, no, common base, excuse me.
Common base, okay. So when you're working on trying to find the frequency response of these, there's 2 things you have to find. You have to find an R and a C. We're just working on the C today. And let's say you want to know the capacitance on C in. So first thing you do is you identify the kind of transistor. And you know that's a BJT. And then you identify the terminal that V ends on. And that's
The emitter.
the emitter. So now you know it's a BJT and you're on the emitter. So you go up to the picture of the BJT and you place yourself on the emitter. And then you look at all the capacitances that are directly connected to the emitter. So you don't have to worry about things in series. You only have to worry about the capacitance that's like stuck into the emitter. So what's that capacitance?
C
C pi. Oh,
C pi. And you're done. Yay. So that wasn't so bad. What about C out?
I have a question.
Okay.
How come you didn't consider like the C overlaps? You just considered the C pi.
Okay. So that's MOSFET.
Oh yeah, you're right.
But you're ahead. You're ahead. You're on to the next question. Okay. So what about C out for the BJT? I know these drawings are pretty bad, but my pen wasn't working today, so I kind of got lazy. It kind of looks like a MOSFET, slightly decapitated MOSFET. Okay, so see out, you're on, you have a BJT and you're on the collector. So up to the collector. What's your C out?
Is it C mu plus CCS?
Yes, so if you're on the collector, you only worry about the capacitances that are directly connected to the collector, and that's C mu and CCS. So C mu plus CCS, and we're done. Okay, how about C in of the common gate?
Oh, okay, common gate. I was sorry.
Yeah, I'm going on theme. I'm going on the pairs because the other ones have little tricks in them. So this one is actually the most straightforward for finding capacitance, even though it's kind of a mess to actually use, but it's capacitance straightforward.
So wouldn't that be the common or the gate drain overlap plus the gate source overlap plus the channel
Okay,
capacitance?
which terminal is the input on?
Oh, except yeah, not the base or not the gate. Never mind then. I was looking the wrong way.
Okay, so it's on the source, right? For the gate, common gate.
Yeah.
So you're here. So what are the how many capacitances are directly connected to the source then? Peace.
Gate source overlap
Okay, we've got gate source overlap.
and CSB.
CSB, yes. And you're done. CSB plus C gate source overlap. And isn't it nice that they actually use subscripts that tell you something instead of C mu and C pi? Okay. All right, you can guess what's coming next. C out. Okay. So actually, we forgot to say one thing. What's the capacitance looking into the resistor or on the connection to the resistor in our world?
0.
0. In real life, resistors actually have capacitance on an integrated circuit. The wires have capacitance. You've got, what you do to make a resistor is you make a square of a material that has a resistivity. Make the square the right size so you get the resistance you want, but that couples to the silicon. It couples to, if you actually make that resistor in silicon, which you can, you just dope it really lightly and then it acts like a big resistor, but that forms a depletion region, and now that couples to the substrate. You can't make a resistor without capacitance and inductance actually. And you can't make an inductor without capacitance and resistance. And you can't make a capacitor without resistance and inductance. So everything is everything. But when you make a component on an integrated circuit, you just try to make it so if you're trying to make a resistor, the resistance is the biggest contributor. If you're trying to make a capacitor, the capacitance is the biggest contributor. Okay, so C out, so 0 for the resistor. So, and we're ignoring wire capacitance and resistance, which exists. So what about C out and going the other direction?
Wouldn't it be CDB plus CDSOV?
CDB plus
Or
CG.
GDOV, I misspoke.
Exactly. Yeah. Okay. So kind of getting the hang of it. Okay. So the next one, I'm going to make you lie, and then we'll talk about Miller effect. So how many of you did Miller effect in 307? Oh no, we lost Raul again. His internet's a mess. Come on back, Raul. So nobody did Miller effect? Okay. In digital, it actually doubles your delay. But I think mostly in 307 and the other sections, you just kind of slap, just somebody gives you a capacitive value and you just work with it or something. Okay. So let's do the, just to make you paranoid, let's do the wrong way first. Okay. So what's your C in here? So first find your terminal. So for a common emitter, it's the base. So what are the capacitances that you see?
C mu plus C pi.
C mu plus C pi. Okay. C mu plus C pi. C pi plus, and I'm going to leave a space here, C mu. And what about C out?
C mu plus CCS.
CCS plus, and we'll do C mu out here. Okay. So what we've been doing so far, that is a great approximation if both sides of your capacitance aren't moving. So if you look at some of these, I didn't say this in the other class very well, but if you look at like CCS, your substrate, remember pin 7 and 14 from 347? Your substrate pins, those were DC values. So, and you get to DC value is a DC value is a virtual ground. It's not moving, so you call it an AC ground, virtual ground. So CCS, this side is never moving. So CCS, if you're on the collector, CCS is it's as is. But if you are over here and you like on a common emitter, base collector, if you're on a common emitter and you move the base, the collector moves a lot. So actually that capacitance that goes between the base and collector, both sides of it are moving. So you actually have to adjust for that. But any capacitance that is to ground or something not moving, you don't need to worry about a multiplier. You don't need to worry about adjusting it. So these are to ground, this is to ground. All those they're always as is. But again, if both sides of the capacitance is moving, then you have to do an adjustment, a multiplier for it. So let's look at that. So if you have, let's make this a little bit longer. Actually, let's move it over. Kinda. Okay. So this base collector capacitance that goes from here to here, and this is your C mu. Okay. So I think I failed in the last section to explain this well, so I apologize in advance. But here we go. Let's do the old equation. First, just to review what this equation does. So Q equals CV. That's your capacitance equation. And what it actually means is it's not talking about anything to ground per se. It's talking about the difference between the plates. So this Q right here is actually the difference in charge between the two plates. And this voltage right here is actually the positive plate minus the negative plate. Okay, so this CV, it's not voltage to ground, it's voltage to the other side of the capacitor. So that good, step one? Okay, maybe, right. So on this capacitor right here, if you make a big change in the voltage, do you see that you'll get a big change in the charge? And that's difference in the charge across the plates. So again, you're saying this one has a bazillion and 1 electrons, and this one has a bazillion electrons. What the capacitor cares about is that there's 1 electron different here, and that's going to tell you what the voltage between the plates is. Okay. So let's see what happens here. I started off on a good direction here. Yes. Okay. So if you have, let's look at 2 cases. Let's say I have some capacitor and I take this voltage right here and I change it delta V. There's going to be some change in charge delta Q. And it only has to change its charge enough to change the voltage across the plates. Right. So let's look at what's happening to the C mu here. And let's say the gain of this amplifier is AV. If I change V in, how much does V out move? So let's say if everything's delta V here, I need a better, I'll call this delta VI. And this is delta V out. It's not very pretty. Delta V out. If this is C mu, then you've got delta VI on one side, and you've got delta VO on the other. Okay. So let's say I change this by delta VI. How much does delta VO actually change?
AV times delta VI.
AV times delta VO. And I'm going to put some absolute value signs around here just because when you look at AV, you can't tell if it's positive or negative. And it's going in the opposite direction. Since this is an inverting amplifier, when V in goes up, V out goes down. Okay, so the change in voltage across here, what if I add a little I? The change in voltage across here caused a change in charge of delta QI. And so that the total net change in voltage across this was just delta VI. This right here, what's the net change in voltage across this capacitor?
Delta VO minus delta VI.
Okay, so but what's delta VO? I agree with you, but
Negative AV times delta VI.
yes, so it's times negative AV times delta VI. And if you get rid of the minus signs and factor out a delta VI, you get delta VI times 1 plus AV. Let me do something here. Let's move these out of the way. Okay, so the the actual change in voltage across the capacitor was actually 1 plus AV times delta VI. Okay. How much charge did you need to make this delta VI change on this capacitor that has this side grounded? I just wrote it over here. So you needed, I just kind of gave you this. I said, if this changes delta VI, then you have a change of delta QI. Over here, what is the actual total change in charge? What does it have to be?
One plus AV.
Yes, so you have your original change in charge times 1 plus AV. Okay, so it needed 1 plus AV times more charge to get up to it, the voltage that it wants to get to. So how much bigger from the V inside, it had to give that much more charge to just change delta VI. So how much bigger does that capacitance look to the input than it actually is? Oh, that's a bad question. So because it had to put a lot of charge on it just to change delta VI, because all the input wants to change is delta VI. But because the other side's going away from it, it has to pour in tons more charge to get up to that target voltage. So how much bigger do you think the capacitance looks like to the input? Because it had to put all that extra charge on there than the actual capacitor. Not said well. I actually did better here on the previous section. But let's say you have a black box and a capacitor. Right here, you've seen that you've had to put 1 plus AV times more charge onto that to just get the same change in voltage as this first example right here. How much bigger do you think, if you just had that black box and you just knew you had to give that much more charge, how much bigger would you think the capacitor is?
1
1
plus.
plus AV.
Yes, exactly. So what happens is if I'm on the input and I'm just trying to change this much, because the other side's moving, on my side, that looks like a giant capacitor. I had to throw so much charge on it just to move up delta VI, because the other side's moving away from it. That I say, wait, no, that's not the size C mu. The amount of charge I had to put on it makes it look like it's a capacitor of size AV C mu. What do you think? Really? Okay. That's better than I did in the previous section. So this right here, it's a trick you can use. If you need a big capacitor on an IC, capacitors take up a lot of area. So you can actually use this trick. If you take a capacitor and take it from the input of an amplifier to the output of an amplifier, on the input, it looks like a giant capacitance. It gets multiplied by whatever the gain of your amplifier is. So you can use a really little capacitor, but it looks like a big capacitor because of the Miller effect. This is called the Miller effect.
Like, how big are those capacitances?
They're picofarads, femtofarads.
Got it.
So if you have a gain of 100, now all of a sudden you've possibly gone up to nanofarads instead.
And are their capacitances frequency dependent? Like their capacitance values change depending on how fast your frequency is?
They don't change on the frequency, but they change on the voltages. So if
Got
you
it.
put a different voltage on a base, you'll actually see a different capacitance, but that math, leave that to the simulator. The equations are just too crazy.
Got it.
Okay. you taking a picture? Okay, well. Okay, so this is called the Miller effect. And here's a challenging one for you. What goes in front of here? Because if I'm on the output and I move delta VO, how much did the input move, first of all?
1 over AV.
1 over AV. So this would be delta VO over AV. So when I put this through here, this would get multiplied by AV and come out as delta VO. So what do you think the multiplier is here? Nobody does this. I just do it because it's kind of fun.
1 over 1 plus AV.
Exactly. Very nice. AV. Absolute value. Absolute value. Yeah, and this one, you know, if your gain's 100, 1 over 100, that's like nothing. So this is usually ignored. Okay, so we have 5 minutes left. How about, we'll call this again, we'll call this a gain of AV. What do you think C in is? Let's see, let's separate the BJT from the,
Wouldn't it be the channel capacitance plus the 2 overlap capacitances? And then
okay.
I'm assuming there's a similar Miller effect for the overlap capacitances.
Yeah, but let's look at this real quick. The substrate here, actually, I shouldn't say that. The gate channel, this is weird. Okay, it's actually considered C gate source in many textbooks. Because all the electrons are kind of leaning over towards the source, you consider it as having the same voltage as the source. So the question is the capacitance from the gate to the source, so gate channel is, you know, again, alternate name is gate source. Is the source moving?
No.
No. So this is just as it is. You don't need to put a multiplier in front of it. Okay. And then let's look at gate source overlap. Here's the gate, here's the source. Is the source moving? Nope, same question as before. These actually end up in parallel. Okay, so gate to source, gate overlap. Now the gate to drain, is the drain moving? You're on the gate, so you want to look at the other side. Yes, it's moving. So the gate drain needs a multiplier. It needs to see the Miller effect. And so your Miller effect, it's the same thing if you move delta V. It's an inverting op-amp, amplifier. It's going to move up by how much? Or move down by how much?
1 plus AV.
1 plus AV. So this is 1 plus AV. Yes. Okay. And your C out.
Gate drain overlap.
C gate drain overlap. So put that over here. C gate drain overlap. What else? It's helpful to have this diagram, especially at first, So if you're on the drain, you see this, so that's the one you got, and then there's one more.
The diffusion
Diffusion.
of the drain.
So C drain bulk, and the substrate, it's always DC. So if you're looking at the drain to the substrate and saying, hey, is the substrate moving? Answer is always no. So this one doesn't have a multiplier. What about gate drain overlap?
Got 1 over the 1 plus AV.
Yeah. So this one is, oops, plus 1 over. You'd think I'd get better using the mouse, right? With all this practice. Okay. We have 1 minute, so it's let me give you one last challenge here. Okay, the question is, let's give you a specific one here. I'll use the same paint thing on Monday. But what is V C in? Sorry, this is a little bit tricky. So, what terminal is the input on?
Base.
Base. And so you see two capacitances. I see a CBC, which is your C mu. And so that's a CBC. You're on the input, so you look at the other side. Is the other side moving? No. So this is just as it is. It doesn't have a multiplier.
So does the Miller effect occur on C pi instead?
That's the question. Does it? We'll do a CBE, which is a C pi.
I guess not, because the gain for that should be 1-ish.
Yeah, but what you're worrying about is the change in voltage across the capacitance. Oh darn, I went over. I'm sorry. But what is the change in voltage across that capacitance?
It'll always be around VB on.
Well, that's the DC. But when you're looking at the capacitance, you're looking for a change in that V. And the V I'm talking about is the voltage across the capacitor.
So is it going to be like 2 C pi? Because it's going to be 1 plus 1.
Let's see. If I move V in down, what happens to V out?
It also goes down.
Yeah, so if it goes down, what's the change in voltage across the capacitor?
Oh, 0.
Yeah, so how much charge has to go on to change it, to not change the voltage? It's a weird way to say it. 0. So this is actually a multiplier of 0. This actually goes away, which is fabulous for frequency response, because you just got rid of a bunch of capacitance in your circuit. Now it can run faster.
Oh, sorry.
Oh, go ahead.
So, but that doesn't remove capacitance, though. It's just less capacitance.
It removes the BE. It removes the C pi.
Okay.
It makes it disappear. Isn't that kind of cool? You don't get any gain, but you have really low capacitance. So that's another reason why these are pretty cool little circuits. Okay. So any questions? So the actual answer for this one is just C mu. Okay, that's I got you for an extra 3 minutes, so that's all I have for today. We'll continue this, and then we'll actually look at cascoded transistors and look at their capacitance, figure out how to find resistance, and then almost done with frequency response. I think actually on Monday we'll finish it up. And then we go to feedback. Okay. All right. I'm off to a thesis defense that I haven't really read. Okay. All right. I'll see you later.
Bye, Professor.
Bye-bye. Did you have a
I
question?
actually do have one quick question.
Absolutely.
I am a little on the very last question of our midterm. One of the things that it asks about is what type of simulation you would do to iterate through a like sweep through a resistance. And I remember doing that, and I'm not sure exactly what it was. I want to say it was doing like a dot measure to find a resistance, but I don't think that's the answer to that problem.
So part of my word is dead right now, so I can't bring it up. But in the way you said it, there was actually a hint to it. So can you ask the question again?
So, oh, is it? So it is just a sweep then?
Yeah.
Okay.
But what kind of sweep?
Parameter sweep?
It is, but that has to be. That's not a simulation type.
Mm-hmm. So I guess just a DC sweep?
Yeah, that DC sweep is kind of misnamed because you can sweep anything.
Oh,
You
okay.
can sweep temperature, voltage, current, resistance. Capacitance won't work and inductance won't work, but anything else you can sweep.
Okay. Thank you. I just got confused by that because I was like, I remember doing that for one of our homeworks, but I couldn't think of what we did to do that. All right. Thank you.
All right. See you later.